These are the answers to the practice quiz on polarity, intermolecular forces, and liquids and solids. Question number 1, Part A. Each row in this table represents two atoms that can form a covalent bond with each other. Each of these bonds would be classified as polar based on differences in electronegativity. Fill in the missing information in the table. So to determine which atom carries a partial positive charge or a partial negative charge, we have to look at differences in electronegativity based on periodic trends. So for carbon and nitrogen, they are located in the same period. Nitrogen is further to the right, so therefore nitrogen would carry a partial negative charge, and carbon would carry a partial positive charge. With respect to oxygen and sulfur, they are in the same group. And since oxygen has a higher electronegativity than sulfur, oxygen would carry a partial negative charge, and sulfur would carry a partial positive charge. You don't need the actual electronegativity values to answer this question. You just need to know the periodic trends. In Part B of this question, you have to draw the complete Lewis electron dot structure for each molecule. This will help you to determine whether or not the molecule is polar or nonpolar. Starting with methanol, CH3OH, if you add up the total number of valence electrons for methanol, it's going to be 14 electrons altogether, because that's 4 for carbon, 4 for the 4 hydrogens, and 6 for the oxygen. Let's let carbon be the central atom in this structure. So we have a carbon with 1 hydrogen, 2 hydrogens, 3 hydrogens, then we have to connect the oxygen, and finally the last hydrogen. If we add up the valence electrons, again we're going for 14. Right now this would be 2, 4, 6, 8, 10. So we still have 4 more electrons, so place them as non-bonding pairs or lone pairs of electrons on the oxygen. So that structure is now complete. For carbon dioxide, CO2, it's going to be 4 plus 6 plus 6, so a total of 16 valence electrons. And if we connect the carbon to the 2 oxygens and we satisfy the octet for each oxygen, now we have a total of 16 electrons. So we can't add any more electrons to this structure, but we can create 2 double bonds. So these are the structures for methanol and carbon dioxide. The next 2 molecules that we have to draw Lewis electron dot structures for are boron trichloride, BCl3, and dihydrogen sulfide, H2S. For boron trichloride, there are 3 valence electrons for the boron atom, and there are 7 valence electrons for each chlorine atom. That's a grand total of 24 valence electrons. We're going to put boron in the center, make our 3 connections to the chlorine atoms, satisfy the octet for each chlorine atom, and at this point that structure is complete. You may recall I've mentioned that boron represents an exception to the octet rule in which the structure has only 6 valence electrons around it. So that structure is complete, and now on to dihydrogen sulfide, H2S. Sulfur is in the same family as oxygen, so therefore this molecule looks identical to water, H2O. Sulfur has 6 valence electrons. Each hydrogen has 1 valence electron. That would be a total of 8. So we have 2 bonding pairs of electrons and 2 non-bonding pairs of electrons. In Part C, we have to identify the molecular shape. Our choices are tetrahedral, trigonopyramidal, bent, trigonoplanar, and linear. For the methanol, if we focus on carbon as the central atom, there are 4 atoms coming off the carbon. That would be a tetrahedral geometry. For carbon dioxide, we have a central carbon atom. There are 2 oxygens. There's no lone pairs of electrons on the carbon, so that is a linear molecule. The shape of the boron trichloride molecule is not trigonal pyramidal, it's trigonal planar. There's no lone pair of electrons on the central atom. And then finally, H2S, dihydrogen sulfide, would be bent because of the lone pairs on the central atom. In part D, let's classify each of these four molecules as being polar or nonpolar. So based on the asymmetry in which all of the bond dipoles do not cancel each other out, methanol is polar. So therefore it would experience at least dipole-dipole forces because it is a polar molecule. If there is a hydrogen directly attached to either nitrogen, oxygen, or fluorine, it would experience hydrogen bonding. So it does, in this case, because of the OH. Carbon dioxide is a nonpolar molecule because the polar bonds are oriented opposite to each other. So those bond dipoles would cancel each other out. And since the molecule is nonpolar, it can only experience London dispersion forces. Boron trichloride is also a symmetrical molecule in which the BCl bond, it's a polar bond, but these three polar bonds are oriented in such a way that they would cancel each other out. So it is a nonpolar molecule and again would experience only London dispersion forces. Finally, we have our bent molecule, H2S. It is polar because of the bent shape. Those two polar bonds would not cancel each other out, but unfortunately it does not have hydrogen bonding. So therefore we have to consider it would be dipole-dipole forces. Remember, the hydrogen would have to be directly attached to either a nitrogen, oxygen, or fluorine to experience hydrogen bonding. In number 2, we are comparing the intermolecular forces and the boiling point for NH3 and pH3. Let's take a look at the Lewis electron dot structures of these two molecules. Each of these molecules will have a total of 8 valence electrons because nitrogen, or phosphorus, has 5 valence electrons plus 3 for the 3 hydrogens. There will be 3 bonds to the central atom, but there will also be a lone pair of electrons on the central atom. So the shape of these molecules is not trigonal planar, but rather trigonal pyramidal. They are both considered polar because of the asymmetry of the molecule in which the bond dipoles will not cancel each other out. But we have to consider why NH3 has a higher boiling point than pH3. We can't talk about the size of the electron cloud because pH3 would have a larger electron cloud. So there must be a reason why NH3 has stronger intermolecular attractive forces. And the reason is hydrogen bonding. So the NH3 molecule experiences hydrogen bonding, whereas pH3 only would experience dipole-dipole forces. Hydrogen bonding in this particular example is stronger than dipole-dipole forces. In our next comparison, we're looking at CH4 and SiH4. Now, we will be talking about the size of the electron cloud in this example. So as far as the shape of these two molecules, they're both going to contain 8 valence electrons total. They're going to have tetrahedral geometry. And since they are symmetrical and the bond dipoles all cancel each other out, these molecules are both classified as nonpolar. The only intermolecular force that they would experience are London dispersion forces. The strength of the London dispersion forces increase with the size of the electron cloud. And we're trying to argue for why SiH4 has a higher boiling point than CH4. So the SiH4 has a larger electron cloud. That molecule is more polarizable and would experience stronger London dispersion forces than CH4. Number 3, the Lewis structure of methylamine is shown in the box below. Draw a second molecule of methylamine and draw a dashed line to indicate the strongest type of intermolecular attractive force that exists between the two molecules. Each end of the dashed line should be connected to one specific atom on each methylamine molecule. Hopefully you can tell that this molecule is polar, and it would experience hydrogen bonding. So we have to show a specific connection between the two molecules for a hydrogen bonding interaction. The hydrogen atoms that are involved in this hydrogen bonding attraction, these hydrogens should be directly bonded to the nitrogen atom. So we can use either of these hydrogen atoms, but we cannot use the hydrogen atoms that are directly bonded to carbon. So I'll show you one example of what would be correct and one example of something that would be incorrect. So here is one way to do it. I've drawn another molecule of methylamine, and I've drawn it in such a way that the hydrogen connected to the nitrogen reaches out with this dashed line and forms a connection to the nitrogen on the second molecule. So this is correct. And to show you an example of what would not be correct, had I drawn a second molecule of methylamine and tried to make the connection between the nitrogen and one of the hydrogens that was actually bonded to carbon, then that would have been incorrect. So once again, the correct way to do it would be like this. In number 4, viscosity is the resistance of a liquid to flow. Compare the intermolecular forces of each substance and predict which one should have a greater viscosity. Again, we're looking for the stronger intermolecular attractive forces. Remember that hydrocarbons are considered as non-polar molecules. So both C5H12 and C10H22 are non-polar hydrocarbons. So they would only experience London dispersion forces, and as I've said, the strength of the London dispersion forces increases with the size of the electron cloud. So C10H22 has a larger electron cloud, is more polarizable, and would experience stronger London dispersion forces. C10H22 would have a higher viscosity. For the next two molecules, you can see an OH group on each of these, so propanol and glycerol would both experience hydrogen bonding interactions, but since glycerol has 3 OH groups, there are more opportunities to form hydrogen bonding interactions with neighboring molecules. So glycerol has stronger intermolecular attractive forces, it would have a higher boiling point than propanol, and it would have higher viscosity as well. Number 5 is talking about the relationship between temperature and viscosity. As the temperature of a liquid is increased, the viscosity of the liquid decreases. Remember that something like maple syrup will pour more easily when it's warm, and it will pour more slowly when it's very cold. So this effect of increasing temperature and decreasing viscosity can be explained as follows. At higher temperatures, the molecules have, on average, higher kinetic energies. At a higher temperature, a greater fraction of the molecules will have enough energy to overcome the intermolecular attractive forces between the molecules. In number 6, we are simply identifying a phase change and then classifying each phase change as endothermic or exothermic. You know these vocabulary words. Solid to liquid is melting. Solid to gas is sublimation. Gas to liquid is condensation. Gas to solid is deposition. Liquid to gas is evaporation, and liquid to solid is freezing. The endothermic phase changes are ones in which energy is absorbed. So you're going from a lower energy level to a relatively higher energy level. It's going to absorb energy when melting, when undergoing sublimation, and when undergoing evaporation. Those are all endothermic, and the reverse would be exothermic. So condensation, deposition, and freezing are all exothermic. They would release energy. All right, moving on to number 7, we have a phase change diagram in which we have a solid that's being heated, that's in segment A, and then the material melts during line segment B. The liquid is being heated during section C. It undergoes evaporation in part D, and then finally the gas is being heated in part E. So as we can see in this diagram, line segment D is longer than line segment B. We have to explain why in terms of intermolecular forces and energy. We're talking about melting versus evaporation. So line segment D corresponds to the enthalpy of vaporization, liquid to gas. Line segment B corresponds to the enthalpy of fusion, solid to liquid. It takes more energy to convert from a liquid to a gas than it does to convert from a solid to a liquid. And the reason is because when you're going from a liquid to a gas, essentially all of the intermolecular forces between the particles must be broken. Whereas in the solid to liquid transition, only some of the intermolecular forces are broken. In number 8, we are given the specific heat capacity of water for each phase of matter, solid, liquid, and gas. We're given the enthalpy of fusion, which has to do with melting, and we're given the enthalpy of vaporization, which has to do with evaporation. In a certain experiment, 90.1 grams of ice is converted from negative 10 degrees into 90.1 grams of water vapor, steam, at 110 degrees. So we have to do each of the calculations in this process. Part A, how many kilojoules of heat are needed to raise the temperature of the solid from negative 10 degrees to 0 degrees? We're going to use the equation heat equals mass times specific heat capacity times delta T. So the mass is 90.1 grams. The specific heat capacity of solid H2O is 2.03 joules per gram degrees Celsius, and the change in temperature is 10 degrees. We were asked to round our answer to 3 significant figures, so we'll go ahead and do that. The answer we get is 1,830 joules, and they want that in kilojoules, so we'll say 1.83 kilojoules for part A. Now for part B, we're not going to use mass and specific heat capacity and delta T because there is no delta T. We're not changing the temperature. We are melting the ice at 0 degrees Celsius. In the table, that would be enthalpy of fusion. We want to use 6.01 kilojoules per mole. So first we have to convert 90.1 grams of water into moles. And using the information on the periodic table for H2O, there are 18.016 grams of water for every 1 mole, and then 6.01 kilojoules of heat required to melt 1 mole of ice. And if we do this math, and our answer will be in kilojoules, rounded to 3 significant figures, we get 30.1 kilojoules. Moving on to part C, we are going to be raising the temperature of liquid water from 0 degrees to 100 degrees. So heat equals mass times specific heat capacity times delta T. The mass is still 90.1 grams, but now we're dealing with liquid water, so we use a specific heat capacity of 4.18 joules per gram degree Celsius, and our change in temperature is 100 degrees Celsius. If we do this math and round the answer to 3 significant figures, we get 37,700 joules. Expressing that in kilojoules, 37.1 1.7 kilojoules. We need another phase change. This time it's vaporization. We're evaporating the liquid at 100 degrees Celsius. So we're not using mc delta T because there's no change in temperature. We are converting from grams to moles just as we did before, and then multiplying by 40.67 kilojoules of energy for 1 mole. And if we do this math, our answer will be in kilojoules, rounding off to 3 significant figures. We get 203 kilojoules. Finally, in the next step, we will be raising the temperature of the gas from 100 to 110 degrees Celsius. So we'll use 90.1 grams, that's our mass. The specific heat capacity of water vapor is 1.84 joules per gram degree Celsius, and our delta T is 10 degrees. The answer we get, rounded off to 3 significant figures, is 1,660 joules, and expressed in kilojoules it would be 1.66. So, we have done all of the calculations for parts A through E, and if we add up the total amount of heat for the entire process, and we're going to round off to 3 significant figures, we get 274 kilojoules. All right, for this next question, we have vapor pressure versus temperature for 4 different liquids. The liquids are propanone, ethanol, water, and ethanoic acid. You can see a dashed line at 101.3 kilopascals. That pressure happens to be the standard pressure at sea level. That's the equivalent of 1 atmosphere of pressure. So that pressure will help us determine the normal boiling point for each of these liquids. So a pressure of 1 atmosphere is equal to 101.3 kilopascals. Estimate the normal boiling point for each of the 4 liquids from the diagram above. All we have to do is draw a horizontal line at that particular pressure value, and wherever it intersects the curve, we go down to the x-axis and we estimate the temperature at which this liquid would come to a boil. So the normal boiling point for propanone is 55 degrees Celsius. The estimated boiling point for ethanol would be just under 80, so I would say 79 degrees Celsius is my estimate. We know that the normal boiling point of water is 100, and we can read that directly from this graph. And then finally, for ethanoic acid, our estimate would be somewhere between 115 and 120, so I estimated 118 degrees Celsius for the boiling point of ethanoic acid. We're still talking about the same diagram, but now the questions have to do with vapor pressure and intermolecular forces. So at 50 degrees Celsius, the liquid that has the highest vapor pressure would be propanone. The liquid that has the lowest vapor pressure would be ethanoic acid. A high vapor pressure is associated with relatively weak intermolecular forces. A low vapor pressure is associated with relatively strong intermolecular forces. So of these 4 liquids, ethanoic acid would have the strongest intermolecular forces, and propanone would have the weakest. The questions in number 11 and 12 have to do with water. Remember that even though water boils at 100 degrees Celsius, that's the normal boiling point, it is possible to either raise or lower the pressure. And if we lower the pressure, we lower the boiling point of water. And if we raise the pressure, we can raise the boiling point of water. So in number 11, if we had a pressure of 50 kilopascals, then the temperature at which water would boil, estimated from the graph, would be somewhere between 80 and 85 degrees Celsius, and I'm going to estimate 82 degrees Celsius from this graph. If instead we raise the pressure, the water would boil at 110 degrees Celsius if the pressure, and again this would be somewhere between 140 and 150 kilopascals. So from the graph, I'm going to estimate that the pressure would be 145 kilopascals. So for questions 13 and 14, we have a phase diagram. The first thing that I tend to do when I'm given a phase diagram is to identify the regions that are solid, liquid, and gas. Let's go ahead and do that. Again, we have pressure on the y-axis and temperature on the x-axis. So these are the three phases of matter identified on the phase diagram. And now in question number 13, we have to estimate the normal melting point and the normal boiling point. So normal would mean let's go to a pressure of 1 atmosphere, and the temperature at which it changes from a solid to a liquid would be the normal melting point. I'm going to estimate from the graph it's somewhere between 30 and 40 degrees Celsius, so I said 34 degrees Celsius. For the boiling point, that would be when it changes from a liquid to a gas at 1 atmosphere. And from this graph, I'm going to estimate that it's between 60 and 70. So I said 64 degrees Celsius. In question number 14, if this substance were at a temperature of 50 degrees Celsius and a pressure of 0.5 atmospheres, again, here are the three phases of matter labeled. If we're at 50 degrees Celsius and 0.5 atmospheres, that would be a gas. If the pressure on the substance were increased to 1 atmosphere without changing the temperature, we would cross over from a gas to a liquid. So gas to liquid, that's condensation. If the temperature were decreased from 50 to 0, holding at the same pressure of 1 atmosphere, now we are changing from a liquid to a solid, that's freezing. And then finally, if we decrease the pressure from 1 atmosphere to 0.25 atmospheres at constant temperature of 0 degrees Celsius, we are changing from a solid to a gas, and that is called sublimation. So once you identify the direction on the phase diagram that you're traveling to, you can tell which phase change is occurring. Number 15, Coulomb's law shows that the force of attraction between oppositely charged ions will increase as the magnitude or the absolute value of the charges does what? Well, there'd be a greater attraction between the ions if the magnitude of the charges increase. In other words, a +2 -2 attraction between ions would be greater than with a +1 -1 charge. Now it says as the distance between the ions, that's going to be decrease. So if the ions are farther apart, they would have a lower attraction, but if they are closer together, they have a greater attraction. And now we have in number 16, 3 compounds: magnesium oxide, MgO, potassium chloride, KCl, and sodium fluoride, NaF. We have to rank them in order of increasing lattice energy. Well, since magnesium oxide is +2 -2, that's going to be the greatest one. That'll have the highest lattice energy. And then of the remaining two, potassium chloride, those ions are larger in size and farther apart. That's going to be the smallest lattice energy. So it's KCl, and then NaF, and finally MgO. Let me go ahead and give complete explanations for the rankings. So in number 17, why is B higher than A? We are comparing sodium fluoride and potassium chloride. It's not about the magnitude of the charges, it is about the sizes of the ions. Now the answer must include a discussion of both. So my first statement is that both sodium fluoride and potassium chloride have the same magnitude of charges for their ions, because they're both +1 and -1. But the ionic radii, the sizes of the ions, would be smaller for sodium fluoride than it is for potassium chloride. And since the sodium and fluoride ions are smaller, they are closer to each other in distance than potassium chloride. And when the ions are closer to each other, they experience a greater attractive force. So to summarize, same charge, smaller distance. In number 18, it's not about the distance, it's actually about the charges. So the ionic radii of sodium and fluoride are similar in size to that of magnesium and oxide. They are similar in size because oxygen and fluorine are in the same period, sodium and magnesium are in the same period, so they are similar in size. We're not changing from a 10 electron shell to an 18 electron shell like we were in question 17. So they're roughly the same size. But a +2 -2 attraction, magnesium and oxygen, those ions have a greater charge magnitude than in sodium fluoride. So ions with a greater charge magnitude experience a greater attractive force. So again, to summarize, sodium fluoride and potassium chloride, same charge, but sodium fluoride is smaller ions. Sodium fluoride, magnesium oxide, roughly the same distance between the ions, but magnesium oxide has a greater charge magnitude. All right, well, number 18, that was the end of the practice quiz. Hopefully you found these answers and explanations helpful. Thanks for watching, and good luck studying for your quiz.